Thank you very much for coming to this first semi-experimental online San Francisco Postgres Users Group meeting. We're hoping that it will all go smoothly and with no technology failures, but you never know. So your forbearance is appreciated. Our speaker tonight is Colton Shepard, and he will be presenting on, well, I'll let him introduce his talk because I'm sure he can do it better than I can. There's only a few announcements. Usually this is the point that we will talk about conferences coming up, and the only one I want to mention is PGCon, which is normally held in Ottawa, Canada, is being held online and starting next week. So you can go to pgcon.org to check that out. And there will be a Q&A at the end. Stacy, do you want to go briefly over what the process is for the Q&A?
Yeah, basically, if you look at the top of your screen, you'll see a little, what looks like a cartoon strip dialog bubble, and that's your chat. Click that, drop down to the send to at the bottom of the box, organize and click organizers only, type your question, and then we'll relay it to Colton so that he's not trying to read 23 things all coming to him at once. So. And we'll be doing Q&A all at the end just to keep things kind of manageable the first time around. So that's it. Any questions about using the chat or the Q&A? Okay, cool.
Great. And with that, I would like to turn it over to Colton.
Thank you. One last thing. Could you make me the presenter real quick?
Hang on just a second. Little details. Now go back over to people. Colton, make presenter. Ta-da! You should now see all your presenter tools.
All right.
And there you are. Woohoo!
All right. Thank you for confirming that this works. So today I'm going to be talking about JSONB in Postgres. I'm going to start with an introduction of what it is, go into why you might want to use it, what sort of use cases you'll really get a good benefit from, and go from there into when you might not want to use it, which is surprisingly enough the hard part of this. And from there, I'll branch out into things like how do you use it, what sort of things can you do with it, what do all the operators in question do, and then more operational concerns like indexing and new Postgres 12 features as well that are less well understood and hopefully should shed some light for the more advanced users in the audience. So before I get too far into this, though, I would like to briefly introduce myself. My name is Colton. I was an employee of Citus Data prior to them being acquired by Microsoft early last year. Now I'm at Microsoft. At Microsoft, I am a Postgres and Citus implementation and migration specialist, for lack of a better term. My official job title technically has me as a ninja, whatever that means. And in practice, what this means is that I'm going to be working with people that have various database workloads, whether it's on Azure, on-premise, there's a few people at the edge, a few people in third-party cloud environments, all sorts of strange setups there. I'm definitely not limited to Microsoft stack here, and just help them get Postgres working to meet their needs. So what that means is that I've got some good exposure to all sorts of odd things, and this shouldn't be specialized to any given environment. Everything I'm saying here should apply regardless of how you're using Postgres in your workload today. So with that being said, I'm going to go ahead and start with what is JSON and what is JSONB, and start from the basics here. So JSON stands for the JavaScript Object Notation Data Interchange Format. I had actually never seen that full description before I did my research for this talk, and I somehow doubt I'm going to say that full sentence ever again, so I'll just call it JSON from here on out. It's defined in RFC 7158. And one thing I've noticed is that it's a pretty consistent implementation across everybody's implementations. Some RFCs have a lot more wiggle room than this one. In practice, this one is as close to universal as I've seen in an RFC. I can't think of anyone really violating it, but I'm sure there's some edge case somewhere that I've missed. As for what it is, JSON is a lightweight, human-readable data format. You can see on the right side of my screen here, if I can switch over to the right tool, I've got an example of an extremely basic JSON object here, just to store a couple examples. For today's talk, I'm going to be using a basic database schema with a lot of JSON elements to represent purchases at an ice cream shop, because who doesn't want ice cream now that summer's upon us? And you can see here, it's a very simple format. We've got opening and closing brackets. We've got a sort of top-level dictionary key, for lack of a better term, just showing the top-level key. We've got a pretty basic array of elements in there, and each one has a couple different key value pairs inside it. Very simple, very straightforward, very easy to write and debug, wonderful to work with. As for how this applies to Postgres, so Postgres actually has two different data types for dealing with JSON in general. One of them, which is just the JSON data type, is where it stores it, for all practical purposes, as a string with some fancy helper functions. It's the old version. I'm not going to be going into much detail on it. It lacks most of the cool features I'm going to be talking about today, and I can't think of anyone that I've worked with that's currently using it in production for any real purposes. The other more important one, JSONB, which is the one I'm going to be talking about today, is decomposed for storage instead of stored as a string. So under the hood, whenever you insert a row with it or update a row with it, it's going to be deserializing it, decomposing it for storage, treating it as more of a dictionary for a language such as Python or something like that than a string by itself. In practice, this means it's much faster to deal with. You can index it in a much more meaningful fashion, and the helper functions are able to do a whole lot more with it. There are a couple disadvantages to this. One of them is going to be your insert speed. Obviously, if it needs to do a large parse of an incoming object when you're loading data, this can lead to a bit higher CPU overhead. In practice, that hasn't been a really big deal for most of us, most of the use cases we see, but it's something to keep in mind. In addition, this can have some disk space implications here, but I'll be going into more detail about those later on down the road. So, now that I've got the basics of what JSON is, I think the most important thing to know about it is, what is it good for? There's a lot of advice on the internet about this. The advice is generally pretty accurate, but I'll go ahead and go over some use cases that I've seen people use that have worked out particularly well here. There's 4 of them in particular that really stand out if I'm going to be specifying them. The most important one is going to be with unpredictable data structures in general. If you don't really have a clear picture, or perhaps a consistent picture, of what the data you need to store is going to look like, JSON is a really good way to approach this. Instead of having some sort of complex column-driven relationship where you have, say, an entry that has a join to a table that defines what the value even is, that joins to another table that says what the value is supposed to mean, or something complex like that, you can just put it into JSON there. I've found this to be particularly useful if your app deals with something like an external vendor or third-party data provider that is liable to change the data structure at a whim without proper notification, which is unfortunately a little more common than most of us would like in this industry. If you're using JSON, then instead of having to change the schema whenever that incoming data type changes or something like that, you just slightly adjust the queries to take advantage of the new fields, or have them dynamic enough that you don't even need to do that in the first place, and problem solved. This also works really well if there's a lot of attributes that are going to be rarely used. One of the things that's going to come up a few times in the more detailed examples I'm giving is going to be sort of event use cases where people want to attach information to events, store metadata about events or something like that. And in a lot of those cases, there's going to be a lot of attributes that are very rarely used. So for example, with a traditional schema and this sort of setup, you might have 50 or 100 columns worth of data. that will only be populated 5 or 10% of the time, and this can be a bit of a pain for management overhead, for indexing, for fast lookups, that sort of thing. With JSON, you can just collapse that all into one column, something like metadata or tags or something like that, and get a much more readable schema and much more maintainable schema. And it works very well if you're not going to be using your attribute, a lot of smaller attributes very frequently. In addition to this, I've sort of hinted at this before with some of the use cases I've mentioned, but there's a design model that is referred to as entity attribute value model tables. It's definitely a bit of a mouthful. In practice, it just means what I was talking about, where to get the full information for a single record, you need to join to 2 or 3 tables. For example, you could have your events table as the event, and then that would join to some sort of event users table, which would have joined to event user logging table or something like that. Not a great example of it, but instead of having complex joins to tables that define and then propagate attributes relevant to an entry in a single table, you can just put it in JSON and make it, once again, just easier to deal with in general. The fourth really good use case here that I will mention is with arbitrary fields with dynamic values. This is pretty similar to what I was talking about with the unpredictable data structures, but it's a little more relevant towards the computational or dynamic application side of things here, where sometimes you just don't want to have that rigid of a data definition. Sometimes a record that you want to make can have 1 entry or 100 entries in them, and they can have no real commonality in terms of what they're storing. And JSON is great for that, especially if it's a slightly messy model and you're expecting your start to pivot or need to change a major part of a feature on short notice or something like that. Works great for arbitrary fields with dynamic values. So to go a little bit into this, I'm going to start with a customer story as well. This is, ironically enough, also a Microsoft customer story, but it predates the Citus acquisition, so I'm counting it as a customer story, even if it's somewhat internal these days. There's a project at Microsoft called VenusDB, and there's a few multi-hour-long talks on it that are pretty cool. But in short, it's where the Windows 10 telemetry data is being stored. For a very brief technical overview, there's end user systems are going to be sending in data. They're going to be processed by a sort of aggregate layer because there's so many connections, you really can't have them be handled by just the database itself. And then they come in JSONB format through just regular copy operations for all practical purposes here. Then there's this big, every few minute sort of roll-up processing aggregation paths, where most of the data is just processed, put into aggregates, that sort of thing, roll-up columns. Most of the individual bits are discarded at this point, and some of the JSONB is maintained for future purposes. Very simple and straightforward here. The advantages this has brought are, well, pretty manyfold. One of the biggest ones that really surprised us in terms of really being a bigger benefit than we thought was there's a lot of different teams that are sending in telemetry here, and sometimes that's not always communicated well in advance. So because this is in JSONB format, though, we don't need to worry too much about schema changes to take advantage of new data formats or anything like that. We don't need to worry about massive compatibility issues. All that we get is some JSON elements that don't really match what we're expecting, and if we write our SQL well, we can put those into a table of unrecognized elements and process them later once we get proper documentation on how it works. So when there is a change that's unexpected, it's really easy to deal with. In addition to this, this is a ridiculously large cluster. It processes 5 terabytes of data a day. It's got 2,800 CPUs in it. So DDL statements take a while to complete for adding a column to a table or something like that. And with JSON, you don't need to do that. So it's much easier to do major maintenance things such as that. This has worked out pretty well, and they're actually building a new cluster about twice the size. There's some talks on YouTube about that are linked later on in my talk. I won't go into too much detail about this. So now that although just to briefly summarize one more time to make it clear why this is so good, the big advantage here is that flexibility. The data itself could theoretically end up in columns of some sort, but the flexibility to just not need to worry about the other teams, to not worry about adding or subtracting columns down the road, that's why it's worked out so well over the past few years. Anyways, on to the less good use cases, for lack of a better term, and I'm going to start with the big one. This entire slide is for that, and that's statistics gathering issues. As I'm sure most of you know, Postgres gathers statistics on column contents and distribution. This is a pretty cool process. It usually works really well. And when you run a query, Postgres uses those statistics to plan how it runs. Things like, will this have a nested loop? Or maybe a full table scan would be better because we need to touch 80% of the rows in there anyways. Things like that, the planner just handles for you. And normally that works really well, but with JSONB, we really just don't get statistics on the JSONB values. It's not going to know how frequent various keys are. It's not going to be able to make intelligent decisions based on, well, I can reasonably expect 10 rows in this table to match this filter versus I can reasonably expect 90% of them to match this filter. And that's been a pretty big performance hit in some of the cases we've seen. We've had cases where we get 10x performance by just, say, turning enable nest loop to off, just to force it to choose a plan it thinks is suboptimal, which gets a little bit messy down the road. This is particularly common when you're filtering on rarely used keys, but there's definitely a lot of weird little edge cases that pop up, and we're pretty regularly surprised by this sort of thing when it does pop up because there's just so many little edge cases it's hard to predict. There is a patch that has been put out, and I've got a link to it at the bottom of this. We've got 3 people using it in production. We're still a little bit nervous about it. We're definitely not deploying it at a very large scale here, but it has definitely helped. In practice, what this patch does is it lets us generate statistics based on function results. And as I'll be showing you later here, Postgres operators are considered functions for the purposes of this. We can use the JSONB operators to get some very good statistics based on that here. Something of an edge case though, so if you're going to try it, test it thoroughly first. As for other less good use cases, there's a few more of note. One of them is fields that almost always exist. I'll be going into a little bit more detail on this on my next slide, but in short, if you have a JSONB element that is present in the vast majority of your columns in a table, then it's probably more efficient to make it a proper column. This is because under the hood, as I mentioned, this is a decomposed data type, so it's going to be storing each and every single key value pair, the full key and the full value for every row in there. And this is bad for disk space. If you have to store the same, for all practical purposes, what would be a column name with a more traditional schema for every single entry in the entire column. We've seen some pretty impressive disk space usage reduction when we switch over to proper columns in certain cases, and like I mentioned, I'll be going into a little bit more detail on that in my next customer story. Another use case that has historically been a bit of an issue here is indexing concerns. And once again, I'll be going into a good bit of detail on here in the future, but not every single JSONB not every query written to take advantage of JSONB can be indexed particularly well. Sometimes you just can't get a good index at all. Sometimes you've got some limitations in what query will be effective because it's just not the same. That may be a concern where you just don't get the performance you want because you don't get the indexes you want. Another one is disk space limitations. As I mentioned, there is some level of storage magnification compared to setting it up as columns. And the same applies to certain index types if you're going to be heavily indexing a JSONB column. In addition to this, there's what I would call unnecessary future proofing. For example, if you think the data type of a column may change down the road and you want to make sure you don't need to do any database changes or anything like that when that happens, in practice, this is a cool idea. We haven't seen a lot of benefit from it because you usually need to change the app to change that over anyways, and DDLs aren't that painful. So to go into a little bit about this, I'm going to talk about one of our customers, Heap Analytics. They were originally supposed to be the host for this event, but that didn't end up working out for some reason. So in short, Heap Analytics is a Citus customer, and their use case centers around event collection. In short, this is a horrible mangling of their use case, and I know it, and I'm sure somebody from Heap is on the call to correct me on the details here, but in short, it's event collection where users can attach arbitrary tags, or at least part of the use case is that. And for the most part, this is a good use case. JSONB is great for these arbitrary tags. A user can just write in for any given event in the entire data set that they have access to. They make up a tag, they enter it, they're done. So storing it in a more traditional mechanism would have been difficult to get good results. Unfortunately, as I've mentioned, the keys are stored in full, so the disk usage was being magnified. For every single tag that was added, they were storing the name of the tag and the value associated with the tag. And what ended up happening was, it turns out the tags, even though they're completely user-submitted, weren't that unique. Most users can only think of so many commonly used names for a tag in general. So they found the top 45 or so keys and turned them into proper columns, and this saved 30% disk usage. Last I heard, they had 1.5 or 2 petabytes of data, so that was not a small amount of disk that was saved. And I've got at the bottom of this a link to their blog where they go into a little bit more detail about this, how they came to this conclusion, that sort of thing. But this is a perhaps larger than most people, but definitely a good example as to what to look out for here. This disk usage magnification, because those tags were extremely common, was easily preventable on this. For another use case, unfortunately, I can't name this customer because they're not a current customer and they haven't agreed to talk about this, so this is heavily obfuscated. In short, their use case centered around, to build on a theme here, a tag-based search engine. And one of the big advantages of this was users could fuzzy match both the fields and the values. You could search for a partial match for a tag name and for a partial match of the value in the tag. And this was a really basic schema. There were basically 1 or 2 big tables, mostly just timestamp metadata, tags, and a couple other things that I won't name here. JSONB was used for all the tags. Everything else was set up with proper columns. And the queries as written were set up to just use like operators against keys and values. So a very obvious simple query that they would be running continuously would be, select star from table, where key is like this and value is like this. The problem was we could index the values. We could create indexes on specific keys in here, but we couldn't create indexes on every key, where we were limited in what we could do. So in practice, this meant we were doing full table scans for every query. And this just killed performance. It was a nightmare. We tried to work with them to move to column-based storage, but it just didn't work out in the end. And this is probably the biggest concern I have in practice when looking at a greenfield system and trying to see whether JSONB is the right choice. Are the indexes going to work? Is the performance going to work? Fortunately, I've got some great tips on indexing later in here, and I did learn a little bit more since then. So there's options, but this particular one's a little bit nasty. So hopefully that's been a pretty good summary as to use cases and the basics there. Now that I've covered the basic idea of when you might or might not want to use it, let's go ahead into the operators. So I'm sure we all know what operators are, even if the term is sort of nebulously defined from what I can tell. It just means stock functions for manipulating and accessing data. I've got some examples on this page. I'm sure we all recognize them. Just basic terminology definition to be certain we're all on the same page here. And JSONB has its own operators. So I don't really know how to pronounce this one, whatever this is. So I'm just going to leave it completely unnamed here. But what this one does is it lets us get the object field by key. And what that means is that, sorry, just trying to close the chat window. What that means is that we can drill into a JSONB element and get what we're looking for. So to make this a little more useful, here's our column name. Here is the top level key in the column, and here is the key one down further, and here's our table name. And what we get from that is we get a quotation wrapped result of the actual value in here. And because we use one arrow instead of two, we're getting this as a JSONB element in its own right. So we can feed this into other queries. We can apply further JSON operators to this. This is meant for internal consumption more than external consumption, although I suppose plenty of people would want to return JSONB elements themselves for more complex use cases. If you give it two arrows, you get something very similar where you see we're once again just drilling in with that. And this time we have two arrows for the final level we're going into there. And we just get it as regular column result, none of the quotes, nothing special here, same value. This is text return, probably what you're going to use if you're going to be actually trying to get data out of a JSONB element in a more traditional fashion. But they're both perfectly viable and very straightforward here. Sort of the most obvious simple operator. The next one I'll go over is, I suppose I could call it a question mark operator, but whoever's on the commit, if there's somebody here that makes these decisions, these probably could use catchier names. So what this one lets us do is, lets us know is, does this string exist as a top level key within our JSON element? So once again, with my ice cream schema here, here's an example of how this would work. Let's see, who ordered a regular ice cream cone? Very obvious thing we want to find out here with this. So I've got my basic query here. Let's look at the name from the customer info field using what we showed earlier. Let's look at the product because we don't care about specific values of it. We just want to see where it has the regular cone as a top level key in here. And it looks like we've got two results because this is a good toy schema here. Looks like John Smith ordered a regular cone with this metadata here. It looks like a scoop of vanilla. And an unknown small child ordered, once again, the regular cone with a little bit more complex of a setup here. Used in this case, it's almost exclusively just used for logic, for filters and basic logical operators. Not much you're going to do with it beyond that, but very essential for more complex JSON elements in general. And there's a few more things we can do with it as well. If we add a pipe, for example, like this, we can say, what orders had one of these two elements in them? The regular cone or our waffle cone here. And we get a very similar set of results. We get one person ordered waffle cone, two people ordered regular cones. Very straightforward here. So if you do question mark pipe, it says any element in the array is, if any element in the array matches, we're good to go here, sort of a or operator for lack of a better term. And question mark ampersand is every element in the array, more of an and operator here. And we can combine these further, obviously, for more complex logic as well. Here we've got, let's see, we've got our loyalty program here in our customer information field. Let's take a look at anyone that has a loyalty program in our purchases here. So once again, we've got, we're just going to look using this from our customer info column, who has loyalty information and who has a loyalty program in there. And we've got two people that are actually using a loyalty program. One person's using the legacy one, and somebody managed to use the competitors. To move on from here, Then the next operator I would like to go into detail on is the app operator for existence, for lack of a better term. This one is starting to get a little bit more complicated here. We're trying to answer the question of, does the JSONB element on the right of the operator exist at the top level of the left element? And that's a little bit to decipher. So here we've got our column name, once again, our customer info column. And here we've got an extremely basic JSON element that I'm just creating by putting a string in there and casting it to JSONB. And all we're asking is there somebody with the name of John Smith at the top level of this element? And the answer in this case is yes, there is. We've got John Smith right here, and order doesn't matter in case anyone was wondering here. And this would not return anything for lower level elements with the syntax we've got here. You can reverse the operator as well to get it to work in the same direction. You see, this is the exact same query. We've just swapped customer info and the John Smith name. Next operator is, I guess, the pound sign. Once again, these do need catchier names, so whoever's on that. And what that does is it gets the values at the path as a JSON object. Well, it gets the values at a path. With one arrow, it's a JSON object. With two arrows, it says text instead. So here's our example again. This time, to make this a little bit more readable here, we're going to get the full customer info field so you can see the full field and understand what we're actually getting out of it. And then we're going to we're just going to drill into this JSON element. So the way this works is first we have the top level key that we want to specify, then we have the next level key we want to specify, and there's the column name, there's the table name. So we want to look at the loyalty info for this. So if we look at the full element, we see loyalty info is right here, which matches up with what we were seeing right there. We see the loyalty number in there. So we should just be returning 23523. And it looks like this is covered by the presentation software, but it looks like we did. Oh, sorry, we're actually looking at the loyalty program. My apologies. And we get the legacy result that we wanted. And if you give two arrows, we instead get the same value as text. So exact same logic here. We're just loyalty info matches up to loyalty info, loyalty program matches up to loyalty program, and we get the result of legacy, which matches the expected result. And once again, this time it's returning as text instead of a JSON object by itself. Very straightforward, very valuable, but a bit of a change from how we were doing this earlier. The JSON paths in general are a very interesting topic that I have not seen a lot of people using in the real world, but they've got enough capability that there's definitely people investigating them. They're just, JSON paths in general are not a widely known concept, and that's something I would like to change. You can see how useful they are here. So that's a basic summary of what I wanted to go over with the operators here. There's more on the Postgres website. This is the majority of them, though. This is what you're going to be using day to day to work with JSON in general, at least up until Postgres 11. I'm going to be going into some more information on what Postgres 12 adds after this. So the really hard part in dealing with JSON, as I've mentioned earlier, is indexing. Some of you have probably tried to index JSON in general, and you might have noticed that not all indexes get particularly good results here. And this varies from operator to operator and from index type to index type. But most indexes have limited coverage in what sort of operators they can let work here, and that might not cover your queries very well. Some index types don't even work here as well, which makes this worse. And when I was trying to learn this topic in the first place, I found that a lot of indexing advice on this applies to older Postgres versions, and web searches like to mix up JSON and JSONB, so it can be a little bit hard to pick out the advice on this one. We've seen a lot of trouble at this stage, so hopefully this helps prevent that a little bit in the future here. So let's start with the basic index that everyone knows and everyone loves, B-tree, which is, as I'm sure we all know, the default index for anything in Postgres in general. So what this one does is we can apply a B-tree index on our ice cream orders table here. We just using B-tree, or even we can omit that, and we can make this work no problem here. And this works to some degree. You can see I've got a very basic query here. I'm running with an explain plan, and I've got it just a simple equality operator because this is B-tree. It's relatively limited in flexibility here, but it worked. We're using an index scan. It's exactly what we wanted to see. Unfortunately, this can only really handle equality, and as you can imagine with how complex the operators I was showing earlier are, that isn't really ideal for accomplishing a whole lot here. It's nice though, it definitely works. We can get more complicated though. Now we can get into functional indexes. For those of you who aren't familiar, you can create an index on the output of a function. In this case, I'm just looking at the name field in our customer info column on this table, ice cream orders. And I'm just indexing that. And it works. Once again, we can just take a look at our basic select here, where the customer info is equal to, where the customer info name field is equal, and we once again get an index scan. This is where most of the basic indexes I have seen show up. If you've got a key that is regularly present, which most people do, and you don't want to make it a first-class column, which is often not done, despite what I mentioned earlier. Excuse me. Then a function index on that particular value on that particular key works just fine. It doesn't let you handle like operators because once again this is B-tree, but sometimes this is all you want. A very fast, simple lookup, and you know what you're indexing here. It's easy to work with. But that's about the most you can really use B-tree for here. So let's move on to less popular index types. Let's try hash, for example. Once again, this is the same as B-tree. Equality only, but, well, I should rephrase. We don't have full like support is what I should say. But we can do the same thing. You can index a function result if you want. You can compare JSON directly. It works. If all you care about is equality lookups, which is certainly a use case we've seen, which is certainly a use case that works, this does the job. You can see once again, we've got the create index using hash this time. And we've got our basic query, just looking at the pure equality on our constructed JSON type, and we've got an index scan. So for function indexes with hash, very similar story here. I've got an example right here. We're creating our index on ice cream orders using hash, and we've got our actual operation here. And then when we do our select that matches that, we get an index scan. Unfortunately, if we try to use a like operator here, we don't get an index scan, even if we have sequential scan disabled, as you can see I did here in my testing here, because with that ridiculous cost. So useful, but I don't see it often, and I don't really expect you to use it often. Let's move on. Gist, FP, Gist, and Brin. The short answer is no. You get something like this. Data type JSONB has no default operator class for access method Gist. In short, it doesn't work for indexing the column itself. You can do function indexes again. It's the exact same thing, just using Gist on our operator, and you get an index scan. And this applies to all of these, Gist, FP, Gist, and Brin. Very powerful tools, but you're limited to function indexes, and that doesn't always do everything we want to here. So let's move on to the last one, Gin. I'm sure some of you have looked into this before, and this is going to probably look pretty familiar. This is, if you have looked into it, this is just a screenshot from the Postgres wiki showing what gin indexes support. And it took me a couple hours the first time I saw this to really understand what was going on here. Admittedly, I was pretty new to Postgres at the time, but I digress. So I thought I'd go into this one in a bit more detail here and try to explain what this means before we get too far. So gin has operators which which give us different approaches for indexing, different capabilities for indexing, and different disk usage for indexing. You can see that we've got a few things here. We've got ArrayOps, which which is very specialized, and I'm not going to go into a lot of detail here. And we've got the two most important ones for our purposes here, JSONB with JSONOps and JSONB with JSONB Path ops. And you can see these add quite a few things for indexable operators. You've seen these operators before. We want to use these. These are going to be the majority of what we're going to be actually using in day-to-day operations. We want them. We've also got TS vector, which is a cool thing, but it's a specialized tool, so I've only got one slide on it. So now for the wall of text. Here's what it looks like when you try to set up a gin index with JSONB path ops. We've got our create index, we've got gin, and you can see we're actually specifying in here the actual operator we're using. We're using JSONB path ops to create the index here. Now, when we try to run our basic queries here, we get much better results. We can use the operator from earlier. If you recall this operator here, we're asking whether this regular cone exists at the top level of our product column. And yep, we get a bitmap index scan. Awesome. We get an index condition of actual JSONB operations here. And we can get a little fancier here. We can deal with nesting. We can deal with more complex logic here. We're still using our index. This is really cool. This operator is incredibly powerful, although has some limitations here, and it's completely indexed here. But JSONB PathOps doesn't do much beyond this path operator here. If you're comfortable with them, if they cover everything you want, it's perfect, but you might need to use JSONB ops instead. That's the default option when you just do it using gin on there. And it looks very similar if you're going to create it and specify it. And here we've got, once again, one of our operators from earlier. We're just seeing, does this regular cone exist at the top level as a key in our product column? And it looks like the answer for here, well, we don't actually have our results of our index scan, which is what we wanted to see. And we've also got nothing aside from the expected special casting here. But we've got, it's clearly using our JSONB capabilities natively here, which is what we wanted to see. And we can use other operators here. We can take a look at this if we want to see one of our queries from earlier, where we wanted to see who ordered apparently a regular cone or a pine cone. It looks like my sense of humor snuck in. And once again, index works just fine. This is probably the best index to use with JSONB in general here. It covers, if I go back a couple slides here, you can see it covers a couple different operators. I've covered most of them in detail here. This should be enough for most practical purposes from what I've seen. About the only thing that this won't cover that I'm aware of is going to be like operators against keys. I have not found a good way to index that. I would love suggestions if somebody has one though. As a special mention, I will point out one more thing. Gin function indexes with gin trigram ops. For those of you not familiar, gin trigram ops is, it lets us do like operators, for lack of a better term, in a admittedly somewhat limited fashion here. For example, with this, I am taking a look at our customer info name field, and I'm indexing that specifically using trigram ops so we can get this like operation indexed. I'll admit this is very situational sounding, but it's got us a truly ridiculous performance boost a few times. You do need to specify the keys specifically, and this only works with like operations on the values. So it is very situational, but it comes up way more than it sounds like it should. So I wanted to make sure this was spelled out as a clear option here. It's cool too. So with that being said, now that that's a pretty basic idea of how to index, and the short answer is just use a gin index. The longer answer is function indexes might work too. So let's move on to how Postgres 12 makes everything better, more or less. What Postgres 12 adds is a new data type called JSON Path. You might recall that on our earlier slides, and I'm just going to go back a little bit here so you can, actually that's too far back, sorry. Didn't think that one through. You might recall on some of our earlier slides, we were handling JSONB paths in a somewhat more complicated fashion here. But now there's a new data type specifically for that. And what a JSON path is it's stored internally as a binary representation of a path expression. And all that means is it's sort of a shortcut for navigating through the entire dictionary at once. For example, you could just give it .key, and what that does is it returns the object number with the specified key. So if we go back to one of our earlier examples here, if you see what we wrote here, we could just do customer info.name with this. Problem solved. You've got some more complex things too, like .star to return all object members at the current level, 2 stars if you don't want to deal with nesting and just want to show everything in there. And you can specify individual nesting levels with that. You can specify array locations, and you can specify all array elements just to decompose the array and not need to worry about array packing and unpacking. That's a bit taken into mind here, so I've got examples of each of these. So let's start with, I should rephrase, sorry. To move on to the JSONB path query. What this does, lets us get what's at a specific path using the syntax we showed earlier here. So here I've got a very basic example of 2 different ways to get the exact same data using what I showed earlier and with the JSONB path query operator. So here we just want to look at the name and our customer info. So for this one, I've got our customer info column, I've got the key I want to look for, and I've got an operator to pick that specific key. And here I've got the JSONB path query equivalent. So we've got our JSONB path query call, we've got what we want to look into, and we're looking at our name. And we get the same results. Once again, these are both returning just JSONB JSONB data types, as you can guess from the quotes here. And it's the exact same results. This is probably the simplest use case I can think of for this. So let's get a little bit more complicated here. Let's look at what happens when you want to see everything at the top level here. So sometimes you just want to decompose a JSONB element, get everything from it, and process that. It might not be efficient, but it certainly is a way to handle messy data types that you don't have the full information on. Sometimes it's just more efficient to write the code that way, even if it looks ugly. Sometimes it is the right solution. Who knows? So to do that, we've got our JSONB path query. Once again, we've got our column in question. And this time we're just using the star operator I showed earlier to return the star path, I should say, to return everything. And we get one result for each element in here. We've got our, we get one result, period. We've got just this array with one element in it. If we give it 2 stars, though, we get both the same array as before. You can see right here. We get the parent level of the whole JSON element, and we get the single child of this array. You can see here we've got the bracket indicating it's an array, and here we don't. And then we get the values further in there. So we get the value of 1 for scoops as its own row, we get the value of vanilla as its own row. This might be a little less practical, but it's powerful. In addition to this, if you want to make this a little bit more readable, you can specify depth when you do this. So in this case, we've got a very similar thing, the JSONB path query. We've got the product column, and this time we've got 2 stars and this bracket 2. And what this means is, let's look at everything 2 layers deep in this JSON element. Nothing more, nothing less. And we get that. We no longer get what we were seeing earlier. If you remember our, our 1 or vanilla, we don't get the parent element like this. We just get everything at that depth. This is a lot more practical, and you can also enter a range of levels. I could have done something like 1 to 3, but that's nearly unreadable as it turns out. So it's useful, but I can't really demonstrate it today. And we can get even more complicated, because what's the fun of Postgres if you don't dive into it deep? So you can index arrays directly in here as well. So same query, but this time we're going to be looking at, for every element in this array, for every element in this JSONB entity, let's take a look at the first element of the array if there is an array. And once again, we get our result. 2 people had their first scoop as vanilla ice cream. Odd choice, but hey, it works. And you can, instead of doing a wildcard, we can just specify at the top level instead. So in this case, let's take a look at our anything that has a top level key of waffle cone, and then an array, and then the first element of that array. And this is what we get. Apparently, the first person to order a waffle cone got 7 scoops of chocolate ice cream. Perfectly sensible. In addition to this, we also have the JSONB path exists operator. This is going to look very similar to the question mark I was showing earlier. What this does is we get a Boolean result as to whether the path exists. So we can look at something like JSONB path exists of our product column, and is there a waffle cone at the top level? And you see for this one result that does have a waffle cone, we get our Boolean. Perfect. This is mostly useful for things like filters on key existence. Here's a somewhat more useful one where it's just where JSONB path exists, but it's good to see what it didn't return as well for demonstration purposes. In addition to this, we do have the JSONB path match operator. You see here, we've got a relatively complex path where we're just looking at anything that has scoops specified in there, and we get this result. You can put very complex logic in here that will output Boolean results. There's definitely a lot of room for complexity in here in general. It's an entire language of its own at this point, though, so I'm not going to go too deep into specific examples. So there's yet another one, JSONB path query array. This is very similar to JSONB path query, but we get an array instead of a series of JSON elements. This is probably a little bit more useful. You can see that here's our original results. We've got 3 different lines of results, 1 for each entry in here. And we can't really tell whether these are from the same query or from different queries here. But with this, we get an array instead, so we can see that this is 1 row, this is 1 row. A bit easier to work with, but might or might not fit your logic flows. You can extend this further to have the JSONB path query first operator, and all this does is it gives you the first matching element. Sometimes that's what you want. You don't need to worry about doing an array and indexing it to 0 or anything like that. Like I guess you could with the syntax we see here with JSONB path query array. You can just get the first one. This one's proved surprisingly useful, but I won't belabor the point. So that's about all I wanted to say. So in conclusion, JSONB is awesome. Postgres is awesome. JSONB is particularly awesome for unstructured and semi-structured data. If you have arbitrary queryable fields, it's a great thing to try. If you have users submittable fields that you want to be able to store in a very clean and readable fashion, it's definitely worth a try. Disk usage planner issues can be concerns. So keep those in mind if you are going to try it out at scale. And it's tricky to index. You definitely have some options, and it gets complex, but you can do it. And of course, if you're running Postgres 12, you get extra advantages as well. And that's all I've got. Thanks for joining again.
Great. Thank you so much, Colton. Yay! Round of applause. So let's see. We do have a question in the comments. I can read it to you or I can paste it to you, whichever you prefer.
Why don't you do both? Let's
Okay.
paste it so everyone can see it and read it out as well.
Okay, let's see. I am sending you the question in the chat window, and it says, what's the proper way to extract numerical JSON data, convert to text and then cast? How will JSON nulls be handled?
So in short, if you use the 2 arrows I showed earlier, it should just return it as if it was a, now that I think about it, sorry, I apologize, I misspoke there. You do need to cast. Yeah, it's going to be returning it as text from what I recall in my testing here. If you use the 2 arrows, you will get text back, so you can just cast it right there and you're all set. And unfortunately, I don't recall offhand how JSON nulls are handled. I'd assume they'd translate to none, but I haven't actually checked.
Okay, so Vlad, hopefully that answers your question. If not, you can let us know. That was the only question we had. There was a comment from Daniel. Here, let me just paste that to you as well, and then I will share it, and maybe it will, let's see, what does it says? JSON has evolved a bit with respect to UTF-8, which is now required. Previously, UTF-16 and UTF-32 were optional, but since RFC 8279, we live in a UTF-8 world.
Thanks for mentioning that. I did not know that.
Okay,
I guess
cool.
I learn something every day.
Yeah, there wasn't a question with it. It was just that comment. So Daniel, if there is a question to go with it, let us know. Anybody else have any other questions? I mean, that was a really thorough and comprehensive presentation. And even as a non-technical person, I was able to follow it. So I was really happy about that. Oh, we have another question. Let me paste that over to you. And it says, in your example of third-party vendors changing their schema as a good example for JSONB, did any migration needs come up?
Trying to think of how to answer this one. Are you talking about migration in terms of data migration or migration in terms of, say, running a migration to change your schema and something like Ruby?
Vlad, if you want to unmute yourself to expound on that.
Yeah, I didn't. Yeah, there we go. That makes it easier. My worry or concern here is if the vendor changes the schema that they're sending you inside of the JSON itself to the extent that like you need to actually change the way that these JSON structures are handled, then all of the old JSON objects in your database all of a sudden are invalid. And so there's like a inside column migration that needs to occur. And I was wondering if that kind of thing has ever come up for you and how that was handled.
So in practice, most of the customers I've seen that anticipate this kind of problem or run into it will have sort of a table or column that has raw incoming data and various other tables and columns where there's processed versions of it. So when this happens, they're just going to adjust the processing logic and probably end up rerunning it for the columns that are unexpectedly different. So it's more of you can store truth, and you can get processing done with the elements they didn't change is one of the big advantages here. For example, if they change one key name, which they do sometimes, so if they change one key name, your processing logic can handle all the other keys. And if you've stored the original data, or like I mentioned with VenusDB, I believe they store things they don't recognize for further processing here. You can just do a second pass on that later. So there is a migration of sorts there, but one of the big advantages here is you can be a little bit more capable of storing weirdly structured things you don't understand for future manual adjustment or process adjustment.
Got it. Thank you.
Okay, and let's see. Igor says, thank you, Colton. Great presentation. So not a question, but kudos. Yay.
Thanks, Igor.
Anybody else? Questions? Okay. Christoph, do you want to wrap up here?
Sure. Let's see. The first one is Colton. I don't know if it flew by on a slide and I missed it. Is there a link to your slides?
No, there isn't. Do you have a way of hosting those, or I'll get that figured out. I don't want to waste the time.
Yeah, we'll sort that out offline.
Yeah, one of the nice things about GoToMeeting is as it records the talk, it pulls the slides and creates a PDF of them. So when we post the video, we'll be able to post the PDF of the slides.
I'll send you the PowerPoint as well if you want.
Okay, great.
Sure.
Yeah, just if you just export the PowerPoint as PDFs, we'll host it. That's no problem.
All right, I'll send it off to you after this.
Okay,
Awesome,
great.
thank you.
And for the attendees, we'll post a link to the video, and as it becomes available, to the video and the slides in the Meetup conversation for this event. Okay, great. Well, thank you everybody for attending. I think this was very successful. The technology was remarkably cooperative, which is always always entertaining. You can look forward to more virtual pugs like this one, and be sure to just enable notifications from the GoToMeeting, or for the GoToMeeting, excuse me, the Meetup group, and because that's where everything will be circulated. And great, and thank you so much for attending, Colton. Or presenting.
Yeah,
my pleasure. Thanks for having me.
Oh, wow. Very happy to get your email. And also, if anybody else is interested in presenting at future meetups, the virtual ones, we're doing virtual for the foreseeable future. They don't have to be evening. We could do lunchtime ones. We could do late morning something. So if you're interested, please contact us via the Meetup. There's a contact organizers, and that you can find us there. And if you have any comments about using the GoToMeeting, also please let us know what worked for you, what didn't. And again, very successful. Thank you so much, Colton. Thank you, Christoph, for hosting.
Thanks very much. Bye-bye, everybody.
Bye.
Farewell.